Hi there. Bringing to you a very, very interesting problem which combines principles of mechanics, geometry, and um, symmetrical tension. So here we see, let me read the problem out to you. Two masses of mass m each connected by a string of length 2a. So this is the string from here, this point to this point. So the string is connecting these two masses, each of mass m, and at the middle point of the string, they're pulled by a force F, this force. What would be the acceleration of the mass m on the left, this one, when the distance of it from the center of the string, the center, let's call it O, when the distance from the center of the string is x. Right now, you can see that the distance is a, which is half of 2a basically. Now, as this force, and this force is vertical, and these masses are constrained to move horizontally on the table, and they cannot move up. So the situation is somewhat like you have a thread and you have a table down, and first the two masses are just on the table, and then you go to the middle point of the thread here and you start pulling it up. So these masses start moving on the table towards each other, right? And I will also make an interactive simulation of this as I make for most of my interesting problems and concepts. And I'll share it with you in the description. But for now, I'll give you a little break and I would like you to try it by yourself. All right. So if you've tried it by yourself, do compare your solution to mine. The way I'd go about this is at any point when the mass has moved a bit, and it is, let's say, reached a point here where it's at a distance of about x from the center, and the force is pulling upwards like this still, and part of the string is moved till here, let's say. The force is still pulling here, and the string has moved here. And in fact, let me put this as a dotted line to show that the string is actually moving in this direction. So as the force is pulling it up, the string has moved here, and obviously the mass has moved from here to here, right? And at this point, the length here, the string length to the left of the center is still a, even though it's now seen as the hypotenuse of this triangle. And let's see how much this thing has moved up using Pythagoras theorem. And let's say this angle is theta. This is root a square minus x square. I hope you'll agree with me on that. And if I extend this line here a bit, right? And again, finish the diagram here. Say the other mass has also moved to a distance of x. And also extend that line here. Now you would see that this angle is 90 minus theta. And so this angle would also be 90 minus theta. And I can see, let's say the tension in the string is T, pulling it here, and T here as well. Now you can see that actually the vertical components of tension are going to add up, and the horizontal components of tension are going to cancel out. These two are going to cancel out, and the vertical components are going to add up. What are these vertical components? So this is tension T, right? And its vertical component is actually, can I see, this is going to be cosine of this angle, right? So T cosine of 90 minus theta. And these are vertically opposite angles. This is 90 minus theta, as this is 90 minus theta as well. And The horizontal component of this is t cosine 90 minus theta, which is nothing but t sine theta. And there is another vertical component coming from this part of the string, which also contributes another t sine theta. So in total, I have 2 times t sine theta. And this is going to be equal to basically the force, because this is the net force upwards. And let's see what is sine theta here. Sine theta is, if you look at this triangle here, it's root a square minus x squared upon a. So from this, I can find out that the tension is equal to F upon 2 times sine theta, and that will equate to this expression. Now let's see what is the force pulling this mass m in the horizontal direction, because we are asked what is the horizontal acceleration of this mass. It's moving, constrained to move horizontally. So the horizontal acceleration of this mass is going to be determined by the horizontal component of this tension. This component. Horizontal component of this tension is t cosine theta, which is nothing but, what is cosine theta? Cosine theta is x upon a, right? So t is fa upon 2 root a square minus x squared times cosine theta, which is x upon a. This is going to be equal to the mass times its acceleration. And this acceleration ax is what we are after. And remember, this is different from this variable a, which is distance. And the last step, I will cancel this a with this a, and I'm going to get f times x upon 2 root a square minus x squared times m. Yeah. And this is going to be the horizontal acceleration of mass on the left. And by symmetry, it's also going to be the acceleration of mass on the right. So this was a very subtle and elegant problem that I encountered, and I thought I should share my solution with you guys. And please feel free to attempt it on your own. And in case of any doubts, please comment. And I will also share my interactive simulation of this concept. And see you soon again in another video. Bye.